Right, then it's a great pleasure to have for our last talk in this afternoon session, Natalie Brown from Quantinuum. That was high-fidelity fault-tolerant teleportation of logical qubits, transversal gates, lattice surgery on a trapped ion quantum computer. Yeah, many of the words you heard yesterday, so this sounds like error correction. It probably has to do with that, but it probably also fits perfectly into the benchmarking session. So please go ahead, Natalie.
Yep. I'm super excited to be here. I did miss the QEC session yesterday. This is definitely going to be a QEC talk. And the reason the title is so wordy is because this is, in fact, the title of an upcoming publication. The official story is it's in preparation, but I'll tell you it's past that in preparation phase. A lot of this work was led by Kieran Ryan Anderson. You have junior varsity playing today. The second author is talking. So we've done quite a lot of fault-tolerant quantum computing at Quantinuum. In fact, if you take away nothing from, or the only thing you take away from my talk, I hope it's that Quantinuum's hardware is uniquely designed to implement a lot of these fault-tolerant protocols early on, which has allowed us to do a lot of benchmarking. Majority of this talk, I'm going to refer to this paper, which was our first demonstration of real-time error correction on a logical qubit. In this work, we looked at a single code block using the Steane code and benchmark a lot of protocols. Since then, we've done a lot of other things, including logical 2-qubit gates, real-time minimum weight perfect matching with just the repetition code, quantum phase estimation on a QED code, physical magic state distillation using a quantum intermediate representation, and other kind of algorithmic things as well. So this is our capabilities roadmap. When I was pulling these slides together, I was kind of thinking of like, what is a good intro slide? And I came across this capabilities roadmap from, I think, 2022. Again, these check marks we had done previously, but we kind of were like, what do we want to do next? And in particular, we wanted to look at higher distance codes and things with more logical qubits, specifically looking at logical algorithms done fault tolerantly. And then really what we have our eye on in the near term is demonstrating different break-even milestones. That's when some logical algorithm, some logical thing, maybe it's a gate, maybe it's a memory, outperforms its physical counterpart. This is where QEC starts to actually get you somewhere. So April has been a very busy month at Quantinuum. We have these 3 papers that are either out or should be out within this month. We have this result in collaboration with Microsoft, where we looked at Bell state preparation. If I would have planned better, I would have talked about this work in the benchmarking session. But here, this work is really interesting because we benchmark not only the quantum Fourier transform, but what I thought was cool is this logical T-state teleportation. So we apply this T-gate to a target qubit many times and see at that survival probability. The work I will talk about today is the first demonstration of state teleportation, and we look at 2 different implementations, including transversal gates and also using lattice surgery. So I really want to get to the experiments and the results, but I think in order to kind of appreciate them, you need to know a little bit about our hardware. If you've never seen a Quantinuum talk before, then this is all new. If you have, then this is really you've already heard all of this, but we use a quantum charge coupling device. This is an ion trap quantum computer, and we use ytterbium-171 ions as our qubit. They have this nice hyperfine splitting, which allows for this long coherence time within our qubit. We tend to talk about ion crystals. This is because we have an ion that is our qubit, and then we have a sympathetic cooling ion that sticks with the qubit ion at all times. What's unique about our system is we have these different regions. So here we have 2 commercial devices. We're really good at naming stuff. So we have one called H1 and another one called H2. H1 is a linear trap. And here we have these different regions where we have a blue interaction zone. This is where all of the gates, measurements, resets happen. Then we have these green zones. These are our storage zones. So we can move qubits out of that interaction zone so they can just sit there and not have any crosstalk from whatever is happening in the gate zone. Our H2 device is very similar to our H1 device. What we did here is we just stacked 2 linear traps on top of each other, joined them together, and now we have this kind of race trap type structure. H1 has 20 qubits, H2 has 32 qubits, but it's expected to have over 50 qubits in 2021. I think you might hear more about that later in the week. And all the work I'm going to talk about today was done on this system, this racetrack type system. So I'm not really going to talk much more about the hardware, but the big takeaway I want you guys to know is that in our system, the qubits move around. So here I have that linear trap, which is the qubits lit up. Here you see them running around the racetrack. This is the exact system that all this work was done. And then we have a test bed where we've been able to show that we can do these multi-species junction transports. There's more recent work where we've shown not only just one qubit like you see here, but actually many more. So what does this get you? Well, it gets you all-to-all connectivity. All of our qubits in our system can talk to all of our other qubits. We have very high fidelities, very low crosstalk errors. But what's the most important for this work is this qubit measurement and reuse and this classical conditional logic. So I can measure my circuit in the middle, measure a qubit in the middle, use that measurement to then conditionally apply gates. And in this way, I can do very dynamic real-time circuits. And this is really important when you want to implement the Steane code fault tolerantly. Okay. This is probably a little bit of like quantum computing 101 for this audience. But now I'm going to talk about how state teleportation works, because this is, again, the algorithm that we looked at. So we're going to start off with Alice and Bob, and they're each going to share one end of a bell pair. Alice is also going to have this unknown state psi on her end. Alice is in Colorado, and Bob's sitting in the audience here. Alice is going to entangle her two qubits, and she's going to measure them out, getting some classical bits of information. She's then going to text Bob, call Bob, give him that information by some classical means. And with that information, Bob's going to be able to apply correction to his bell pair, or half of the bell pair. And by doing this, they teleport this state over. So you're able to do this non-local quantum state teleportation. So why is this important? Well, you could imagine as we scale up, you're going to have to connect different modules. So if you're able to send one bell pair to each of the modules, you can then teleport states between the two modules. In particular, in an error correction setting, this is also how you can do Neal-style error correction, syndrome extraction. So, and what's unique about that is you use this bell pair to transversely measure your syndromes. And so you don't have to measure things d times. It's single shot error correction. So this could have some time savings in your system. And then finally, this is probably the most important, I think, in QEC, is you can modify this protocol to now not just do state teleportation, but gate teleportation. And this is probably the most common way we think of how to do non-Clifford gates in QEC codes. You prepare some resource magic state, and you can teleport it in using only Clifford gates, and in this way, do non-Clifford gates on QEC codes. So what does the circuit look like? Here's our basic physical circuit. We have that bell state prep here, and then a bell state measurement. And then finally, we have these classical controlled corrections. And when you run this circuit, you teleport this unknown state psi from qubit 1 down to qubit 3. So this is what the physical circuit looks like, or the logic, if you will, that we're trying to implement. So what does now the equivalent logical circuit look like? So the first thing we're going to do is replace our physical qubits with logical qubits. In this work, we use this Steane code, or this 713 color code. So we need 7 physical qubits to create one logical qubit. And this is a distance 3 code. That's where you get 713. So it should be able to detect and correct any single error that occurs on the physical qubits that make up it. Any single physical or measurement error. So we went from a 3-qubit algorithm to now a minimum of a 21-qubit algorithm. So next, how do we do these gates logically? Well, there are a few different ways you can do gates, but probably 2 of the more famous ones, if you will, are transversally and lattice surgery. I think transversal gates are a little bit more intuitive to understand. And in transversal gate, if you have, say, code block A over here, let's say it has 5 qubits, and you have code block B over here, also has 5 qubits, you're going to line up those physical qubits that are alike and put them together and implement the gate. So if I want to do a C0 between code block A and code block B, that amounts to just doing 5 physical C0s between my 2 code blocks. They are naturally fault tolerant. What that means in this context is if I have an error on my index finger, it spreads at most to 1 error over here in this other code block. But it's worth noting you will still need QEC gadgets to be able to maintain the coherence of your logical qubits. And then no QEC information is given. I'm just simply imparting the gate. Lattice surgery is a bit more complicated. Logical gates are performed by doing these kind of joint Pauli measurements. What you kind of do is you take your 2 code blocks and you merge them into a bigger code block. And through this, you're able to manipulate the information and do logical gates. They can require an additional code block to perform gates. The C0, for example, you typically need 3 code blocks, one that's a logical ancilla. But the advantage here is you essentially perform QEC while you do the gate. You do a bunch of different stabilizer measurements, which then gives you information that you can feed into a decoder. And so you kind of get two bangs for your buck, where you're doing the gate and you're also getting QEC. The other main advantage to lattice surgery is it requires only nearest neighbor connectivity. So you can do this in a fixed planar architecture. Okay. So in this work, we looked at 5 implementations. I know there's only 4 here, but I'll explain that in a second. We looked at the physical. That's exactly what it looks like, just doing this 3-qubit algorithm. Exactly that. We looked at the transversal case where all of the C0s and any single qubit gate are done transversally. And then we looked at it both with this QEC block in there and both with it out. So that's why that box is dashed. Then we looked at 2 different flavors of lattice surgery. So the first one, this MXXMZZ, is the analogous circuit, just replacing the gate set with a lattice surgery gate set. And then another advantage of lattice surgery is because it's kind of a brand new gate set, you can compile your logical algorithm a bit differently. And this can have some overhead savings. So this circuit actually does the same logic, but you'll notice it's a 2-qubit logical circuit as opposed to a 3-qubit. So let me walk through how we perform the transversal case. So a lot of the work, I mean, all of the work I'm going to talk about today really relies on this initial paper. In this paper, we kind of did a lot, but we basically demonstrated all of the single qubit components needed for this code. So we did initialization fault tolerantly. We did multiple rounds of QEC fault tolerantly. We did real-time decoding using a lookup table. And so rather than going through all these individual pieces, I will cite this paper or refer to these protocols a lot. I'll go over them very briefly, but if there's anything that you don't understand, it's 100% in this paper. Except for the transversal 2-qubit gates, it's in a different paper. Kind of just lied to you. So, okay, so the first thing we're going to do, well, the first thing I want to say actually is that in this work, we're always going to treat the Bell state prep, or the Bell state, I should say, as a resource state. So we will at the end post-select on this resource state being implemented correctly. So first we're going to encode or initialize our 2 logical qubits we're going to use for the Bell state prep. We do this by using an encoding circuit. The encoding circuit looks like this, and it's a 2-step procedure as outlined in this paper by Goto. And the first part, you run this half of the circuit, which non-fault tolerantly encodes the logical Z0 state. And then you have this weight 3 logical, non-destructive logical operator that you measure. And in this way, you're able to catch higher weight errors that would make this circuit non-fault tolerant. So let me say that a little more clearly. This first half is a non-fault tolerant encoding, but if you add this logical check at the end, it makes it fault tolerant. You can implement this as a repeat until success. So if this check goes off, you can actually just reinitialize everything and start over. But because we're treating the Bell state as a resource state, we're only going to do this once, and we'll post-select on this measurement at the end. The next thing we're going to do is that transversal Hadamard. That's, again, self-explanatory. We're just going to do Hadamards on all the qubits in the code block. Then we're going to do the transversal C-naught. That's, again, just doing a C-naught between all light qubits. And then we're going to move on to a syndrome extraction cycle. I want to differentiate what I mean by a syndrome extraction cycle versus a QEC cycle. Here, I'm just going to run these two sets of circuits. These are measuring all 6 checks in our code, but it's not enough information to actually correct. It's only enough information to detect. Now, this is okay because I'm going to treat this as a resource state. So I only need to know that there was an error. I don't need to be able to correct it. Now that I've prepared the resource state, I'm ready to move on to what I'll call our target qubit. It's the one that has the state we're going to teleport down. And I'm going to do the same thing, but this time, because I'm not going to post-select, I'm going to go ahead and do that repeat until success up to 3 times. Again, I won't post-select on this measurement at the end. If for some reason I failed, I just move on with life, and that's how it goes. Next, I'm going to rotate to whatever logical Pauli basis state I am preparing. This is, again, just a transversal operation. And now in the 2 different versions, I either move on to the next step or I implement this full QEC cycle. So in this full QEC cycle, this is a very dynamic circuit. And what I'm going to do is I'm going to measure these flagged checks. This is a scheme by Reinkart where I use ancilla qubit acting as a flag on another ancilla qubit. Sometimes we call these flag scillas. So the checks flag each other. And if any of these syndromes are non-trivial, I move on immediately to measuring the unflagged checks. And through these 2 pieces of syndrome information, I'm actually able to distinguish all weight 1 errors within this code. If these measurements are all 0, I move on to measuring the second set of checks. If they're all 0, then I have no information to correct on, so I'm done. But if they're non-trivial, I move back up here and measure these checks. This, again, is outlined in explicit detail in that first paper. Finally, the rest is relatively straightforward. I apply that transversal C-naught, a transversal Hadamard, and then I do a destructive measurement out. From this destructive measurement out, I get 2 valuable pieces of information. I get what my logical operator is, and then I also get enough information to reconstruct my syndromes that I can then feed back into a decoder, decode in real time, and apply that correction if necessary. So in these experiments, real-time decoding occurs here if the QEC cycle was done, here and here both times, so up to 3 times within the circuit. From there, I'm able to know whether or not to apply these gates, but in principle, what I do is I just update my Pauli frame. So I keep track of this in software. If you can avoid touching your qubits, that usually is best practice. So in this, I'm going to post-select on that Bell state. I've already said this, but I'm only going to post-select on either that verification step, so that weight 3 logical operator being non-trivial, or any of the syndromes being non-trivial. There's no other post-selection done in this experiment. Okay. The lattice surgery implementation is very similar. In fact, I prepare the logical qubits analogously. And then what is different is I do this now lattice surgery gate set. So here I'm measuring a joint weight 6 stabilizer. So you'll see I have A, B, 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 is qubit 4, 5, 6, 4, 5, 6. So I've kind of merged these codes together, measured this joint stabilizer. I'm then going to measure the syndromes once. Again, this doesn't give me enough information to correct, only detect, but that's all I care about in the Bell state. That completes the preparation of the Bell state, so I can move on to my target qubit. Again, I measure or prepare it in the same way as the transversal case. And then what is different is this MZZ lattice surgery operation. It's very similar to the MXX, but now I've just I use my control Z's instead of control Z's instead of control X's. Same thing, joint stabilizer measurement. And this time I do this full round of QEC. This part is a bit more complicated. I do exactly what I explained before. But then if for some reason one of the checks is non-trivial, I actually will repeat just that syndrome extraction protocol and treat this last round as ideal. This is probably more in the weeds than I should get into for this talk, but it's again inspired by this Reinhardt scheme. And it's just how you can catch things fault tolerantly and do the right thing. The rest is analogous. I'm going to measure out, I'm going to decode, and I'm going to keep track of all these corrections via a Pauli frame. The only post-selection done here is, again, the logical verification step, and then any trivial syndrome in the MXX thing. So if this syndrome goes off, or if the flag goes off, or in that syndrome extraction cycle, any of those syndromes are non-trivial. Finally, we're almost to the data, I promise. We do this MZZ one. This exact circuit was also done by the Innsbruck group a little bit earlier. They looked at distance to surface codes, but they did this exact same state teleportation circuit. And then finally, I point at this paper by Daniel Latinsky. He really looked at how you can reduce overhead using different lattice surgery techniques. So that's kind of what we were trying to demonstrate here. Seeing that this circuit is equivalent to this one over here really relies on this circuit identity. I think I will just kind of skip this, but the point is if you apply that identity, this circuit identity, insert an identity, regroup CZs to make them C-naughts, and then notice that these Hadamards stabilize a Bell state, you get back to the original circuit. So they are logically equivalent circuits. Okay, now to the good part. So if you want to compare physical to logical, you really should be assuming that you have the same underlying error model. And our system is very dynamic. I can load in, 1 qubit and do a 1 qubit algorithm. I could load in 32 qubits and do a 32 qubit algorithm. And when I do that, I have different ions in the trap. The dance of the ions is different. And so the noise model is different. So in all of these, we actually have different number of qubits implemented in the trap. And this is for various reasons. So for the physical one, we run 4 parallel copies. It's a 3 qubit algorithm. 4 times 3 is 12. So there are 12 physical qubits in the trap. And this choice of 4 was motivated by the fact that we have 4 gate zones in the trap. For the transversal sets, we had there were 2 implementations, one with QEC and one without. The one without QEC cycles only had 28 qubits. The other one had 30. For lattice surgery, you need a total of 30 qubits. And then for the 2 qubit lattice surgery, you need 20. So there's different number of physical qubits within each of these implementations. And so here are some of the numbers. The average of the parallel copies for the physical process fidelity was about 98%. Notably, for the transversal case with no QEC, we saw about 99%. But when you add in that big QEC cycle, it drops down to about 97%. And then the lattice surgery ones are a bit lower at 86 and 88%. Here's a bit more detail of the data. So to calculate these process fidelities, we measured all 6 Pauli basis states. That's what these colors are here. And then this box is the average process infidelity, average state infidelity. And then the gray bar is the process infidelity that's related by this equation. So what we see here is that our noisiest states are our Y states, our best states are our Z states, and this is very consistent with the error model we see in our system, where Z states tend to be more robust because we think we suffer from more Z-type noise. And that's why Y is the worst, because it suffers from both bit and phase, and Z is the best because it doesn't suffer from this phase noise.
Yeah. So what was the state that of the logical qubit that's being teleported?
We teleported all these states. Yeah. So we ran those different experiments, and we ran each one of them 6 different times, and so that's what you're seeing here.
Can you say a word about what is the acceptance rate of your initial first state preparation? Like, what is the fraction of runs that contribute to that data?
I should have looked that up before this talk. It wasn't crazy, but I don't know off the top of my head. I can get back to you. Any other questions on this? Yeah.
Are there differences in overall runtime that would also be? I mean, like, I guess I'm asking, what impact does coherence or like open system dynamics have in this?
Yes, that is.
It seems like the lattice numbers are really, really.
Yes, that is a really great question. So the like official answer that I'm supposed to say. It's also true. It's not just official, it's true. These transversal circuits, we've been working on for a while. So they are highly optimized. We have looked at every, move this here, do this. It's maybe not as good as we could be, but it's really optimized. These were thrown together last minute. So they are not optimized in any way. We were excited to be able to do the lattice surgery. We're trying to show the diversity of gates we can do on the system, but one is highly optimized, the other ones aren't. The less official answer. I did the gate counts on these because I was thinking like you, like that's like kind of bad compared to how good the other numbers are, right? And especially like here, this is kind of a skinny circuit, if you will. This one in particular has a deeper circuit on average than this. I say on average because we're looking at dynamic circuits. And then the other piece to the puzzle, which is exactly what you're asking, is that these circuits are all going to get compiled differently, and there's going to be a different number of transport steps per iteration. And that changes also because it's a dynamic circuit. And so I think the answer to why these are different beyond just one's optimized and one's not is circuit depth and transport steps. And we have not explicitly calculated the transport steps for these.
Well, just so that we're crystal, so you're saying that it's transport steps, and is there any role of OCT or pulse compilation at all, or is the subunits of CNOTs, for example, like the primitive that we're being compiled to?
So I tend to think of CNOTs because I don't think of like this pulse level control. So there's certainly something in play here, but we program all of this like at a higher chasm level. So we don't have like, without going into the lab and working with the experimentalist directly, like, so we could think about doing stuff like DD, for example, and improve stuff. But no, this doesn't do any type of, I would expect techniques like DD would help a lot and that kind of thing.
Better than one correction?
So okay, it's a good question. I like to describe no QEC as encoding. So this is just encoding your information at the logical level, doing logical gates, but not actually measuring syndromes. So it's significantly less circuit depth. Every time you add in a QEC cycle, you're injecting noise. And so you're removing this very noisy component. We actually think that the QEC cycle itself is the noisiest component because it's really nasty looking. So not doing this performs better than doing this.
Do you do any post-selection when you don't do the syndrome extraction, or no post-selection?
We don't do post-selection when we do the QEC cycle, no, because this is our logical information that you're in theory not allowed to post-select on. We only post-select on the resource state.
So just two related questions. One is, what's the typical shot count total for these different schemes? And also, if there's a variation in that, is that a potential explanation of maybe drift in the system that leads to lower performance?
Yeah, that is a really good call out. These all do have, because I said that this was like highly optimized and these were kind of thrown together. These ones have significantly less shots right now. I actually think that's probably not true anymore, but I haven't been back home in a while. These ones had like thousands of shots, and these ones had like hundreds. So I think that also kind of accounts for some stuff. All right, let me just I'm like on the last slide, and then I'm happy to take more questions. I'll make my TED Talk really short here. There is a fad in QEC right now, which is taking a QEC code and looking at it as a QED code. And it used to really piss me off because you can't really do that. I don't know that I've become a believer. That's not the right way I would say it. But I have started to see the value in looking at QEC as QED. Hear me out for a second. I can always benchmark a code as a QED code, meaning that I can run my QEC, I can measure out at the end, and then I can post-select on non-trivial syndromes. And what this allows me to do, besides really drive up my fidelities, is actually look at the number of logical errors that my system is giving out. So if I can't detect an error, that's a logical error. That's an uncorrectable error. That's something I would be, that causes me trouble, right? That's what actually kills the logical fidelity. So one way of looking at these numbers is if I had a perfect decoder and I could fix everything in life, which is never true in practice, these are the kinds of numbers I would get. So we do have QED code or QED statistics in the paper, and this is again just post-selecting on everything, and you see we get a couple extra 9s. I think the best way of viewing this is not, oh my God, they post-selected, it's not fair, and their fidelities got higher. I think it should speak to how good the system is and what we could maybe hope to achieve through better decoding, better procedures, all of that. I'll go into questions now. I just want to point out Mike Fosfeg's talk. He will talk a lot more about the hardware. One thing I didn't get to talk about is how do we program these circuits? They're incredibly deep logical circuits. We use something called PECOS and PECOS SLR, which stands for Simple Logical Representation. It allows us to kind of meta-program at this high logical level, and all the QEC is done under the hood. We checked more boxes, and it takes a village. All of these people are employed by Quantinuum and all get Quantinuum paychecks. Yeah, and in particular, I want to shout out to Kieran Ryan Anderson, who did a lot of this work, Dominic Lucetti and Alex Cherniguzov. They were on the software team that really helped implement some of the logic that is necessary to do the QEC primitives. And now I'm done. Actually, I lied just because it kind of goes back to your question. The thing that I usually end on is that we tend to not take hero data. So all of the work I showed in all of our previous papers, we run on a commercial system alongside customers. So that's why we don't do pulse level control. Things would certainly be better if we did. But I think that's kind of a nice thing that we are in some sense. I'm in some sense not an employee. I'm a super user of the computer.
Thanks, Natalie. There were a few more questions. One.
Very simple question. So with error correction and without error correction, we had a different fidelity, right? If you just divide that and take the ratio, does that match with the state preparation fidelity of QEC or whatever the expected value?
So if I don't answer your question well, then ask it again. But I just want to clarify something. When I say no QEC here, I don't mean that there's no QEC. I mean that we don't do this gadget. So this still does error correction because at the end, when I measure qubits out, I get syndrome information that I can decode on and apply correction. All it means is I don't do that nasty circuit. So I don't know if that changes your question at all.
No, what I mean was the dotted box is only at the beginning. Then what basically changes the state preparation fidelity at the logical level. Then losing a circuit, this QEC box,
yes,
you can just push out to the left. So it's like a state preparation circuit.
Sure.
Right?
Mm-hmm.
So in some sense, the fidelity of no QEC case and one QEC case should factorize in principle. I want to see whether that's actually the case.
Yeah, I mean, that's something we haven't looked at, but that would be interesting to look at.
How long does it take to To collect 1,000 shots.
Like clock time? I genuinely don't know the answer. And even if I did, I wouldn't be allowed to say.
I think you can go to Kieran's first paper. Some of these time budgets are in there.
Timing analysis. We do timing analysis in this first paper. We talk about the clock cycle for this. One of the reasons I don't know is because we run our jobs interleaved with customer jobs. So this data took, 2 weeks to get, but it's not just like being ran, right? It stopped and paused and so, but if you want to know the clock cycle, it's in this paper.
More questions?
Over here.
Yeah, Steve.
Thanks for a great talk. And I want to just come back to these comments you were making at the end about quantum error detection versus correction. And sort of the counter argument, and here I'm channeling a bit of this talk that Jung Won gave here a couple months ago, that when you're post-selecting on those sort of trivial syndromes, you're missing the really important but often more deleterious logical errors that come about from I measured an error and I did a correction and there's still something residual. And that those things are something that we want to capture as well that will be missing from this error detection mode. So I don't, just in your conversion over to being interested in error detection, what do you think about that?
So this is like, I think one of the reasons I say like, oh, in the perfect world, like this is what you get. That's not even true, because you're also still going to have like errors. Even if you had an optimal decoder, you still wouldn't be able to get this high. And yeah, I think that's a really good call out, that like QEC itself, even if you're doing it well, and even if you have good physical error rates, is going to still inject error. You're always going to make some mistake in the decoder. You're always going to misread a syndrome or pick, hey, I thought that this was the syndrome I should trust, but I should have really trusted this one. And and that won't be reflected in here at all. Yeah. I think I'm debating how to get like too political here. I think it's a fad to do this, because look at how, for example, the number jumps from 86% to 96%, and that makes all the marketing people go like, oh, your machine's so good. But of course there's major caveats. But as a scientist, I go, okay, that's great. There's a lot of errors that we could have been correcting that we're not. And so what's going on in this circuit? How do I optimize it further? So in that sense, it does give a little bit of like a benchmark of like where, hey, we're really doing bad here. So where can we leak out more wins?
All right. Then I would say let's close the afternoon session. Thank Natalie again. And then I look forward to seeing you all again tomorrow at 9:30 for the Quantum Algorithms Day with a nice introduction by Ashley.